Then, luckily, we do not have to simulate for many of these different kinds of analyses because there is software that will do it. It used to be the case that, that there was dedicated software just for this. I think still in SPSS, for instance, there is nothing that says something about sample size. In fact, for a long time, this program here is freeware actually, G-star power, and it only calculates sample sizes for different kinds of designs. It was the only thing that was there. And there are here and there online sample size pages, which are a bit risky because you never know what they implemented, so you get an answer, but you have no clue if it's true. And since I think version 12 or so from Stata, we can also do this in Stata. And one other one that I want to mention, just because it's relatively easy, if the program is called PS for power and sample size. Also, it does nothing else than power and sample size calculations. It's also freeware for Windows, by the way. That G-star power is also for a Mac. And that stuff will also work quite well for the simpler designs. Okay, we'll obviously go with Stata because we all have that. If you have, by accident, a very old version of Stata, version 12, then you should upgrade because the commands change a little between version 12 and 13. So there might be a couple of people around who still have that. Make sure that you upgrade to, well, 13 at least, or just use the 14 that we have online. Yeah, then again, you see that if you want, you can go through Stata's graphical user interface. Where under statistics, there is a power and sample size, and then you get here all the different kinds of power and sample sizes that there are. And over there, a way to try and find the one that you actually need. So if you know that what I want to do is something that is related to, well, needs, if you click there, then here you only are left with the ones that are about needs. It's actually way easier to simply remember the command, as usual. And that is what we will do. All the Stata examples that we will go through here are about comparing two groups. And let's see. First, let's try to recreate what we did before in our simulations. This is the command that we'll use. Power two means. What are two means? 115 and 120. Because we're comparing two means here, basically we're assuming that we are comparing two interval scale variables. For that, we need to say something about how wide the distribution is. The standard deviation was 10 in our case, because I know that this is a standard deviation IQ. And the power that I want is 0.9. I think if I leave this out, Stata will assume by definition a power of 0.8, which I find a bit on the low side. So you have to add power equal to 0.9. And then you get this estimated sample size for a two-sample means test. A t-test assuming that both of these standard deviations are equal in both of the groups. If you want something else, different standard deviations in both groups, that could work too. Then you type there SD1 10 and SD2 20, if that's what you want. And then you get back, well, an alpha, 0.05, you didn't mention that, but this is what Stata is assuming if you don't mention it. Power of 0.9, well, we ask for that. Delta, that's the difference between the two means. The two means itself, the standard deviation, so basically all this is what you inputted already, besides the alpha value. And the estimated sample size, 172 or 86 per group. So that's in one go the actual answer that you need here without going through all kinds of complicated simulations here. Typically what you are trying to figure out if you do this in practice is, how large should my sample size be and how bad would it be if I do a bit less, or how much would I win if I do a bit more. And command allows this by, for instance, asking for this, give me power 0.6, 7, 8, and 9, so that I can compare how much better it gets as my sample size increases. And here you see, where we have that, total n, 82, all the way up to 172. And here, these are the subpoints for the groups, for increasing power. So the more certain I want to be, the larger my sample size is supposed to be. If, for some reason, sampling is very cheap, and I might want to go above 0.9, even to 0.95 or 99, who knows, then I can calculate also how high it should be, that sample size. If you're not even sure, for instance, about what that standard deviation here is, and also not so sure about the extent to which it matters. Oh, did I have that? Yeah. You can even ask that. So give me a list for different power values and for different standard deviations. So then depending on what I find there, I can consider how reasonable it would be to, for instance, triple check here what the standard deviations are. Now obviously a table like this is not very intuitive, and if you add the command, the option graph behind it, you get these same numbers, but now in the graph. So here you see on the vertical axis what the sample size is supposed to be. For instance, if you know how much budget you have in terms of time and money, then you can already see, well, let's say the best that I could do is, for instance, 300. Then you know exactly what it is that you can accomplish and what it is that you cannot accomplish. And if you figure out that 300 is simply not enough to have a decent chance to find something, then just don't start it. Do something else. Come up with a different design or research something else, and that would be just fine. But don't start it and then in the end find that you get nothing, simply because the sample size is too small. Okay, now let's see if we understand what the what's called the comparative statics are. If the standard deviation rises, well then what? Let's see, standard deviation goes up from here to there. Right, so the orangey line is the largest standard deviation, and the bluish line is the smallest standard deviation. So we see that the bigger that standard deviation is, the larger the sample that we need, which makes sense. So we're comparing two normal distributions. If I have two normal distributions with a small standard deviation, so that's it, and another one there, that's easy to compare. So a sample size need not be that big. If I have two sample sizes, two standard deviations that are really large, that means I have humps that are really wide. They overlap to a large extent and makes it more complicated to find differences between the two. So the fact that these lines are higher for larger standard deviations is not so weird. And obviously, well, what happens if power rises here to the right, then we see also that these lines go up. Power is how certain you want to be, and you obviously find that if you want to be more certain, you need a larger sample. Also not so weird. Okay, let's try a couple of these differences to see which kinds of numbers matter here. This one. The difference that I looked at was 115 versus 120, and actually the only thing that matters here is the difference, not where they are. If I'm comparing two of these humps, if I take both of them and I move them somewhere else, I'm trying to find the difference between the two, it doesn't matter. Okay, so if you look at 100 versus 105, that's the same delta of 5, you'll get exactly the same result, and understandably so. Also, if you are a bit more lenient, let's stick to an alpha of 10%. Don't, but if for some reason somebody would suggest this, then you'll see that the sample size goes down. Also for obvious reasons. But easiest is forget about this. We don't want an alpha of 10% at all. Who would want that? And every once in a while you could argue it's reasonable, but you open up yourself to the argument, yeah, you just added a larger alpha to make sure that your effects fall through. Now indeed you find effects that you wouldn't have found if your alpha would have been 0.05. So forget your argument about why it is reasonable and just stick to the 5%. Okay, one other one. Thus far we looked at a t-test where we're just comparing group 1 and we measure the mean and group 2 and we measure the mean. Let's see what happens if we have one of these other t-tests. And one of the other t-tests that we had was a t-test that was paired. So I have two measurements, let's say your IQ before I injected you with some weird concoction, and your IQ afterwards. Okay, so you are your own control in a way. I measured your IQ before and afterwards. And here you see part of the data was 114 before, and after the injection it was 121, and 103, 136, 99, 110. Now we see here, first, if I have a correlation here between these two measurements of 0, these measurements are not related at all. That is basically saying we do not have a paired test. That's basically saying we have two different groups and they are not related at all. So in that case, I get an n of 87, and my total sample size would be 87 times 2, because I have to measure 2 times for every person in the data. So that is the same as what I had before in the case where I didn't look at paired means. Now let's see what happens if my correlation goes up. Here I have correlation from 0 to 0.2 to 0.4 to 0.6 to 0.8. And you see here on the vertical axis what that does to your sample size. And you see clearly that sample size then goes down. Okay, so the higher the correlation between these measurements, the more I can, let's say, get rid of larger samples. Now let's see why that is. Here, that whole idea of these paired samples works because you are your own control. If I'm just trying to figure out, is that serum working, and I ask for, let's say, 100 persons, I measure their IQ, okay, go home. Now I ask another 100 in the lab, I inject all of them, and now I measure IQ. That would be a t-test that is not paired at all. I have here a group and I have there a group, that's it. Now I look at you yourself. You might have a really high IQ already, very likely, 145. And now if I inject you, you get, let's say 5 higher, 150. That 5 works for you, but you are already quite high. If I have measurements that are, where the correlation between this left column over there and that right column over there is high, then the fact that you are your own control is working very well. I'm taking into account that I'm doing something on you twice. So all the quirky stuff that is inside you there and inside you there. And if I subtract the two, let's say all the mess inside you gets deleted. I get rid of all the noise. This is why within subject design is usually very useful. And the higher the correlation here is 0, and it doesn't help. But if it's 0.8 or so, then the sample size will go down dramatically. That really, really helps. There's a small caveat here. If you look at this in more detail and take into account something that we don't do now, that these things over there themselves are measurements and therefore not precise, then this benefit from the paired t-test gets way smaller than it appears now. So do realize that it sort of look like a total wonder here that we are decreasing our sample size from 87 all the way down to say 20%, which is dramatic. Well, in practical terms, it's not really that good as it appears here. But still, the paired samples is actually working well for us. And at least we should be able to see here that indeed for higher correlations you get smaller samples in general. Let's see, that's the comparison of the means. There's one other command left, and that is the comparison of the proportions. Same thing, now instead of two means, we type two proportions. The example that we had was 0.3 versus 0.4. Once again, we type power 0.9, otherwise Stata will assume that we mean 0.8. And we get here, well, let's see, our alpha of 0.05, our power of 0.9, the difference, delta of 0.1 here, and the two separate probabilities that we are comparing. And that leads to a sample size of here, 954. Okay, we find 950. Expensive to be able to find the difference between 30% and 40%, apparently. Now, let's see. One thing that is missing here is that there is no standard deviation. So for the t-test, we needed that. We needed the two means and the two standard deviations to say something about how wide the distribution is. Here we don't, and there is a reason for this. And that is, well, if I have something binomial, then the expected number of yeses is n times p, if p is the proportion. So if p is at 0.3, it is 1,000 times 0.3, or if we're flipping a coin, then we expect 1,000 times 0.5 or 500. And the standard deviation, so how wide the distribution is something like this, the square root of n times p times 1 minus p. Forget about what that exactly means, but it is completely defined by n and p. I need nothing else. So for binomial stuff, flipping a coin and so on, then the standard deviation is defined in terms of that p and that n itself. I need no other number. So if you there assume 0.3 for p, then I know what the standard deviation is going to be, even without you telling me anything. So here you have our example, the coin toss, 1,000 times 0.5 is 500, and the standard deviation is 1,000 times 0.5 times 0.5, 50.8, and that could give us a range of, let's say, reasonable numbers that we could expect here, 469 all the way through 531. Okay, anyhow, so this is why we do not need any standard deviation statement here. Okay, so let's see, we had this, and that led to that. Obviously, if we're trying to compare not 30 versus 40%, but 60 versus 70, we get exactly the same thing, which is should be totally obvious, because the only difference between this one and that one would be recoding all the ones to zeros and all the zeros to ones. That doesn't change a bit to the whole problem itself. So it's not so weird that both this one and that one lead to exactly the same number over there. Okay, just a recoding difference. However, here it starts to be different. You might be tempted to think that this difference of 1 is actually completely defining the whole thing, just like the difference between 115 and 120 was for the t-test. Here is different. Here you see, for this difference over there, 0.1 to 0.2, which is also a 0.1 difference, we see that sample size, the necessary sample size, decreases actually. So when we are with something where we are comparing stuff near the edges of 0, 1, so either close to 0 or close to 1, then our sample size can be smaller. Here, this is actually where, this is the worst place to be, so to speak. If you want to compare 0.45 to 0.55, again, a 0.1 difference, but now around 0.5. Now this is the worst place, 1,048. And one way to get that is if you go back to this one. Here you see that standard deviation that determines how wide the confidence interval is. You see that this, if you maximize this is maximum, p equal to 0.5 as a maximum right in the middle. So the standard deviation is widest. You get the widest confidence intervals when we are near 0.5, and it gets better as we get near the edges. So it's easy to mix up. In the t-test, there, 115 versus 120, versus 105 versus 100, or 50 versus 55, none of that matters. For the proportions, it does, and quite a bit. Okay, so what do you need to know about this? You need to know first of all, the commands, of course. You have to know how they work and which number to look at, and that this is really 524 per group, and that the total n then would be 1048. And besides that, you need to know the different options that the commands have. You saw already a couple, and there are actually a couple more, and understand in which direction the sample size changes dependent on these parameters. So, bigger difference, okay, sample size will go down. Smaller difference, sample size will go up. Standard deviation, bigger, sample size will go up. These kind of things you have to know by heart as well. Okay, two-sided tests and one-sided tests. The number one rule to remember, okay, let's stick to two-sided tests because that's the safest. One-sided tests assume that you have a clear idea in which direction the alternative hypothesis is going to go. So I suspect my coin is showing heads way too often, and I want to check if it really is any different from 0.5, and the only reasonable alternative that I have is that it is larger than 0.5. That would in principle be an argument to use a one-sided test, but the standard counter-argument to actually using this would be, well, if you depend on that argument to find an actual difference, then yeah, you have to be really, really sure that you thought about this argument up front and not afterwards. Okay, if you say, okay, let's put all the probability mass, all the 5% on one side, and then my hypothesis is rejected as I wanted, then yeah, you might be susceptible to other people thinking that you are committing fraud. Let's see how this goes. Let's see. Yeah, this is the one t-test example where, in fact, you see an example where Stata gave different kinds of tests, one-sided in one direction, one-sided in the other direction, and this is two-sided. So there I said simply focus on the one in the middle, that's the only one to look at. Another one here too, Fisher's exact, we'll give you a one-sided Fisher's exact. Do note that the number there typically goes down, so if you want to find a significant difference, it's easier to look at one side because each number gets below 0.05 faster. So that would, in principle, help you, but whenever Stata gives it by default, it will be two-sided, and the suggestion is to stick to two-sided. You can ask for one-sided test if you really insist, and then you will see indeed smaller, one-sided will deliver a smaller sample size. So one-sided is, let's say, good for you, and because it's by definition good for you, we typically don't do it, and we stick to two-sided.